time always runs the same way. It never goes backwards. Now we're aware of time because we notice that things happen one after another.
Time stands as one of the most perplexing phenomena in the cosmos. We experience it as an unchanging, continuous force, always progressing, never pausing or reversing. But what if this perception isn't entirely accurate? What if, under the right circumstances, time could move backward? What if scientists have, for the first time, witnessed negative time? The concept of time has intrigued both scientists and philosophers for centuries. From ancient Greek philosophers speculating about existence to Albert Einstein's groundbreaking theories of relativity, our understanding of time has undergone massive transformation. Despite these advancements, time has always remained a one-way journey. That is, until now. Scientists at the forefront of quantum physics have made an extraordinary breakthrough. They have observed phenomena that suggest negative time, moments when time appeared to flow backward. This revelation challenges everything we previously understood about the nature of reality and could have major consequences for the future of physics, technology, and our grasp on free will. But how can time move in reverse? And what could this mean for our everyday lives? To explore these questions, we must venture into the strange, often mind-boggling realm of quantum mechanics. In classical physics, time is understood as an irreversible path. This concept is tied to the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases. This principle accounts for why a broken egg doesn't spontaneously reconstruct itself, or why a cup of coffee doesn't spontaneously return to a hot state after being mixed with cream. Such experiences solidify the idea that time flows only in one direction, forward. However, in the quantum world, things are far less predictable. Quantum mechanics, which explains the behavior of particles on the smallest scales, defies common sense. Particles can exist in multiple states at once, teleport over vast distances instantly, and now, apparently, even experience time moving backward. The groundbreaking experiment that led to this observation involved manipulating quantum systems in extremely controlled environments. Scientists used ultra-cold atoms and finely calibrated laser pulses to create settings in which quantum particles exhibited behavior that contradicted the expected forward flow of time. One of the primary elements behind this discovery is quantum superposition, the idea that a particle can exist in multiple states simultaneously until it is observed or measured. Researchers found that under specific conditions, these particles could be induced into a state where their wave functions evolved as though they were retracing their steps, moving backward in time instead of forward. This reversal of expected events is what scientists are calling negative time. To make it clearer, picture a game of billiards. You strike the cue ball, and instead of continuing forward, it reverses its path back to where it began. This is what was observed at the quantum level, albeit in a far stranger and more perplexing way. One particularly striking aspect of this finding is its connection to time reversal symmetry in theoretical physics. Time reversal symmetry proposes that the fundamental laws of physics should behave the same whether time flows forward or backward. While this doesn't occur in classical mechanics, in quantum mechanics, time reversal symmetry has now been detected under specific circumstances. This raises some profound questions. If time can reverse itself at the quantum level, could this principle apply to larger systems? Could we, in theory, develop technology to manipulate time? While these possibilities are purely theoretical for now, the observation of negative time is a significant step in understanding what might be achievable. One of the most exciting applications of this discovery could be in the field of computing. Quantum computers already operate in ways that defy traditional logic, and the discovery of negative time might open new avenues for processing information. If time can be controlled in quantum systems, it could lead to advances in error correction, computational speed, and even entirely new methods of data processing, potentially unimaginable today. Furthermore, The implications for our understanding of causality, the relationship between causes and effects, are profound. In our everyday experience, causes precede effects. You flip a light switch, and the light turns on. But what if, in some quantum systems, effects could occur before causes? While this might sound like something out of science fiction, researchers are now considering the possibility that negative time could challenge our most basic assumptions about the sequence of events in reality. Beyond the realms of physics and technology, the discovery of negative time also raises deep philosophical and existential questions. If time isn't strictly linear, does that mean our past, present, and future aren't as fixed as we once believed? Could this discovery pave the way for new interpretations of free will and determinism? If the future is not set in stone, could it be possible to influence events in ways we had previously thought impossible? Of course, this doesn't mean that time machines will be developed anytime soon. The effects observed are at a minuscule scale, and translating these phenomena into practical applications is still a challenge that scientists are only beginning to address. However, just as quantum mechanics led to revolutionary technologies like semiconductors, lasers, and MRIs, the discovery of negative time could lead to future innovations that we cannot yet comprehend. As research progresses, physicists will continue refining their experiments, testing new theories, and pushing the boundaries of what negative time could reveal about the universe. This discovery is still in its early stages, and much remains to be understood. But one thing is clear: the observation of negative time represents a paradigm shift in science. It forces us to rethink how we view reality and opens up possibilities once thought to be purely speculative. So, what does all this mean for us? For now, it's an exciting peek into the deeper workings of the universe. It serves as a reminder that our understanding of reality is far from complete, and new discoveries could reshape the very laws we thought were unchanging. As we continue to explore the frontiers of physics, who knows what other astonishing revelations await us? The universe is vast, mysterious, and brimming with surprises. The discovery of negative time is just one more example of how little we truly know and how much there is left to discover. The future of time itself might be far stranger than we ever imagined. For centuries, humanity has been fixated on understanding time. From ancient sundials to modern atomic clocks, we have measured, studied, and attempted to unlock its true nature. But what if everything we thought we knew about time was wrong? What if time doesn't merely move forward, but can also flow backward? It sounds like something from science fiction, but recent experiments suggest that negative time, or time flowing in reverse, might be more than just a theory. Scientists have observed something that seems impossible: a system behaving as though time were moving backward. If this is confirmed, it could radically alter our understanding of physics, reality, and even the future of the universe itself. But what exactly does it mean to observe negative time? Could this be the key to time travel? Could it explain strange quantum phenomena? And most importantly, how might it change the way we perceive the past, present, and future? Let's break it down. The arrow of time. Why time moves forward. We experience time as a constant forward march. We are born, we age, and eventually we die. A glass shatters into pieces, but those pieces never reassemble into a whole. A cup of hot coffee cools over time, but it never spontaneously reheats itself. This phenomenon is known as the arrow of time, a concept in physics that explains why time moves in only one direction and not in reverse. The arrow of time is closely linked to entropy, a measure of disorder in a system. According to the second law of thermodynamics, the total entropy of a closed system always increases with time. This explains why things break apart instead of coming together and why heat flows from hot to cold, not the other way around. Entropy offers a solid explanation for why time appears to move forward. But what if, in some situations, entropy decreases instead of increasing? Could this imply that time could flow backward? For decades, physicists have debated this idea, But now, for the first time, experiments have provided direct evidence of negative time. The groundbreaking experiment that reversed time in a quantum system has made this possible. So, how did scientists observe negative time? The answer lies in the strange world of quantum mechanics, a branch of physics that deals with the behavior of particles on the smallest scales. Researchers at a leading quantum computing laboratory conducted an experiment using IBM's quantum processor. Quantum computers work using qubits, which, unlike classical computer bits that can only be 0 or 1, can exist in multiple states at once. Scientists created a basic quantum system and observed how it evolved over time. In a typical quantum system, the state would continue to become more disordered, following the rules of entropy, just like a broken egg or melting ice. However, using a special algorithm, researchers applied a unique operation to the system. In this case, instead of becoming more disordered, the system reversed its evolution, returning to a previous state as if time itself had moved backward. This wasn't simply a computer simulation, it was a real, measurable effect. The quantum system behaved as if time had rewound, defying everything we thought we understood about the natural flow of time. Implications. Did we just discover time reversal? The experiment indicates that, under specific quantum conditions, time doesn't always move forward. It can also flow backward. This raises mind-bending questions. Does this mean time travel could be possible? Could we use this principle to create a time machine? And if time can move backward in quantum systems, might it also happen in larger systems, perhaps even in the real world? Negative time and quantum superposition. The notion of time moving backward isn't entirely new. Certain interpretations of quantum mechanics have suggested this possibility for decades. One notable example is the Feynman-Stukelberg interpretation, which proposes that antimatter particles are simply regular particles moving backward in time. In this view, when a particle and its antiparticle annihilate each other, it could be seen as a single particle moving forward in time, then backward, and then forward again. Similarly, quantum superposition allows particles to exist in multiple states at once, meaning they might not be constrained by the same fixed timeline as classical objects. Some researchers have suggested that at very small scales, time itself might be bidirectional, able to move both forward and backward simultaneously. This experiment may have provided direct evidence for this concept, showing that, under the right conditions, time reversal is possible at the quantum level. What about the grandfather paradox? If time can flow backward, does this open up the possibility of paradoxes? One of the most famous time travel paradoxes is the grandfather paradox, where someone travels back in time and prevents their grandfather from meeting their grandmother, thus preventing their own birth. If they were never born, how could they have traveled back in time in the first place? While such paradoxes make time travel seem impossible, the latest findings suggest that negative time in quantum systems might not allow for paradoxical events. Instead, it could reveal a new way of understanding time, one where the past and future influence each other in ways we don't fully understand. Could negative time help solve the mysteries of the universe? Another exciting possibility is that negative time could help solve some of the greatest mysteries in physics, particularly the puzzles of dark matter and dark energy. Dark matter, the invisible substance making up around 85% of the universe's mass, remains largely mysterious. Similarly, dark energy is the unknown force driving the accelerated expansion of the universe. Some physicists speculate that dark matter and dark energy might be linked to hidden dimensions of time, regions where time behaves differently from our normal experience. If negative time exists in quantum systems, could it also exist on a cosmic scale? Could entire galaxies be moving backward in time relative to us? If so, it would completely change our understanding of the universe.